So, once we finished with our introduction of organic photochemistry, this lecture we will be trying to concentrate on reactivity of N pi star. Okay. So, for understanding reactivity of N pi star, for a model compound we will take a ketone system. Okay. You can always extrapolate that ketone system N pi star chemistry to other system also. For understanding in a better way, we will take a carbonyl system as a model for understanding N pi star chemistry. I take a carbonyl compound. Okay. Okay. Now, what happens, for example, I am taking my carbonyl compound and trying to shine a light of 310 greater than 310 nanometer. So, what I feel is that basically I am trying to do an N pi star transition. Okay. So, so your N pi star transition will be that 2 electrons which we are talking, non bonded electrons will be on your oxygen atom, right. So, once it gets excited, so you have a non bonded electron on the oxygen atom, this is your oxygen, and you get an electron get excited to your pi star, right. Now, I am asking, like, there are 2 electrons, one it is a non bonded electron on the oxygen atom, another is your pi star electron. So, which of this among these 2 electron, which electron will be reactive? Which electron will be reactive to the reactions? It says that pi star electrons. Any others? You have only 2 options, right? One says pi star, you can say another non bonded electron. Okay. So, any disagreement with pi star? Okay. At least one says it is a pi star electron. We will see what happens. See, you have an electron. I will just draw the, we will see the an R. So, this is your non bonded electron on your oxygen atom. This is your N pi star. This is your pi star electron. If you carefully see your pi star electron will be distributed across your carbon and oxygen, right. If you see your non bonded electron, it will be more on your oxygen atom. Your pi star electron will be distributed between your carbon and oxygen, and your non bonded electron will be on the oxygen atom. Shall I write that pi star is between CO here? And you know that your oxygen is an electronegative atom. It does not want to have an radical on its top. It does not like it, immediately it wants some electron from there, right. So, now you can guess, right, it will be your non bonded electron which will be reactive, comparing your pi as well as your pi star. If you take a pi star as well as you take a non bonded electron on oxygen, your non bonded electron on the oxygen will be the reactive electron. So, can I say that your N pi star chemistry will be dominated by your non bonded electron on the oxygen atom? Can I make that statement? Your N pi star chemistry is dominated by Then we come to this statement. Any doubt here? Because your pi star is now distributed between carbon and oxygen. So, you cannot find that for reactivity, but your non-bonded electron is on the oxygen atom, and your oxygen atom is an highly electronegative. So, it does not want to have an oxygen atom, right. Can you guys tell me a model compound where your oxygen atom has a radical? Any model compound? Yeah, any model compound, I am asking compound. Your alkoxy radical, right? This will be a very good model compound, right. If I say a non-bonded electron, it will be your alkoxy radical, will be a best example. You can take that best example, because you have studied about alkoxy radicals, that is why I am saying. Now, what we will do is that we will take your known alkoxy radical and see that what chemistry this alkoxy radical can do, because you have studied that chemistry. Once we see that chemistry, then we will take that and fit it to our carbonyl chemistry, because you will know then how it fits in. For example, what I am saying is that I take an alkoxy radical. Okay. So, if in the environment of the alkoxy radical, okay, if there is an electrons, if it is there is an electron from a non-bonded. So, alkoxy radical sees an electron somewhere in its environment, a non-bonded electron. So, what it does? Immediately it grabs that electron, right. It can be a reagent, or it can be a substrate, or it can be a solvent. Anything, if it sees a non-bonded electron, immediately it grabs that. That is the idea in alkoxy radical, that is what you studied, right. Then what does alkoxy radical, from where it can grab an electron? From your pi. If you have a pi system, pi electrons available in the environment, it also grabs that. Same way, if you have a sigma, yeah, sigma, the thermodynamics comes into the picture, which radical has to be generated more, and but anyhow it also grabs an electron from your sigma also. So, your alkoxy radical can get an electron from your non-bonded electron, pi electron, and sigma electron. That is what you studied. Okay. That is, I am not telling the new thing. Okay. If I write it with the reaction, then I hope that you will remember that. For example, I have an alkoxy radical. I have a trialkylamine in the system with my alkoxy radical. What does alkoxy radical does? It can abstract an electron from your nitrogen, right. This non-bonded electron it can take. So, you can get R so what is this reaction called? What do you call this reaction? Acid base. What reaction is this reaction is called? Yeah, you call it a electron transfer, or you call it nice reaction it is. It is a redox reaction, right. It is a very good redox reaction. So, this is the best example for your alkoxy radical abstracting an electron from your non-bonded electrons. You can see another good example where your alkoxy radical if you have a pi system in this, okay, it also has an habit to abstract that. This is a good polymerization reaction. you have studied, right, alkoxy radical is a good initiator for polymerization reactions. So, you have an alkoxy radical, if you have a pi system, it can abstract an electron to give me a very good initiators for carrying out many polymerization reactions. So, this is for pi system. So, you have seen that it can abstract an electron from your non bonded electron, it can abstract an electron from your pi system. Maybe your alkoxy radical. It can abstract an electron from your sigma also. See, in this case, you can always say about the thermodynamics comes into the picture, which radical is formed. Otherwise, if it is not a stable radical, it is not going to abstract. Okay. So, that is based on your earlier knowledge on thermodynamics. You have to decide whether it will abstract that electron or not. Okay. This is abstraction of electron, sigma bond. This is inter. You can also, it does intra also. What is that famous reaction you remember on intramolecular? If you are an alkoxy radical. I have studied this reaction, what it does, what product I can get. Right. So, I get my so this is also abstracting from the sigma bond, but this is within the molecule. One is inter and one is intra. These three reactions you have studied, okay, you call this as an alpha cleavage. You have studied these three reactions: alkoxy radical taking an electron from a non bonded, which is your redox reaction; alkoxy radical reacting with your pi system, which is a type of polymer initiator reactions; then alkoxy radical abstracting an hydrogen to form another radical, or alkoxy radical does an intramolecular hydrogen abstraction to form you the alpha cleavage reactions. So, this 4 you have studied very clearly. Now, what we do this, we just take this system and fit with our n pi star reactivity, because this we know what we have studied from earlier knowledge. So, we will just take this and fit with our carbonyl chemistry and see what happens, because our system is similar like that. So, you have a ketone, if I say with my spin, with spin I can say like this. Okay. So, this will be just like your alkoxy radical. If I just use like this, if I say that I am going to write this part as this, looks like your same like your alkoxy, right, most of the time. So, now I can say that my ketone also does the same chemistry. It can also abstract a electron from my non bonded electron n. It can also abstract an electron from my pi. It can also abstract an electron from my sigma, both inter as well as intra, and see that reaction how it works. First, we will see that if I have a ketone, it gets little bit different name when you do the reaction, but if you have this system, same way I am taking an alkyl and so it can abstract this. That is why I said that this radical does the job. Okay. Only the electron on the oxygen atom will dominate your n pi star chemistry. That is what we studied initially. So, you can worry about this part more. written O minus plus. This we call as electron abstraction reaction in carbonyl. This is your first n pi star reactivity. Okay. This is the electron abstraction reaction. Just I am taking my alkoxy radical idea and just fitting with my carbonyl chemistry. That is all. I am not doing anything different here. So, we call this as an electron abstraction reaction. Alkene, then you know this chemistry works, your oxygen. So, what you get? You get an RCO. You get this, right? Pi system. So, this we call as addition to double bond or addition to pi system, this reaction. So, first reaction we saw is an electron abstraction. The second reaction we are seeing is addition to pi system. So, that is how we are going to move on. See, every 3-hour class I am going to take one reaction and we are going to do, first we will try to understand some aspect about some theory aspect, then 2 hours we will be doing only the problems related to electron abstraction reaction. Then we will go to addition to pi system. We will see some, because it happens addition to pi system, if it is an electron deficient alkene, then the chemistry is different. If it is an electron rich alkene, the chemistry is different. So, for 1 hour we will try to understand the theory part, then next 2 hours we will try to do all the problems, like that we will move. Okay. This is our second reaction. The third one which we have studied is, I can take separate paper for the third. You have an R C R X. This is very important reaction, which many things happens in this. This is your hydrogen abstraction reaction that commonly happens in your organic photochemistry. It tries to abstract, for example, I am taking a reaction and doing in toluene. Okay, you can see that they go and abstract a proton from the toluene. That commonly happens. So, this is very important reaction you have to remember. It is hydrogen abstraction. This is from your non-bonded electron, right. So, first we saw one on this is on sigma, non-bonded pi and sigma. Sigma, this is inter, we will see intra. Intra is just like your alkoxy radical. If you have a system, if you can generate a system like this in carbonyl chemistry, okay, then you end up with this type of products. That this is alpha cleavage reaction. You can see a lot of reaction this happening in photochemistry. This most of the time this is the one which predominates. You take your any ketone, try to do, for example, you have studied Norris type 2 reaction. It happens Norris type 2, immediately it will also give you a alpha cleavage reaction. Carbonyls are very prone to do that chemistries. Okay. So, this is another important part. So, you have like basically we have seen. Another one reaction is your energy transfer, okay, which I can write. So, the last one will be your energy transfer reaction. So, if you see your organic photochemistry n pi star reactivity, there are 5 reactions. One is your electron transfer, another is your energy transfer, then addition to pi system, hydrogen atom abstraction reaction, and alpha cleavage reaction. So, what we will do is that we will take each reactions one by one, we will try to understand, and there are like n number of problems you can do in each reactions. It will be always, it will be nice that today I am taking an alpha cleavage reaction. So, most of the time you will get the right product, because you know it is an alpha cleavage product. Okay. But when it comes in combination, then only you have to figure out really whether this reaction goes alpha cleavage, or it tries to go for hydrogen abstraction, or it will. So, there only the most of the time the confusion comes. When it is alpha cleavage, you know that yes, I am going to do alpha cleavage problem, right. So, what I will do is that in that case, when I go to pi system, I will try to include some alpha cleavage reactions also, so that you can understand and like differentiate that this goes by alpha cleavage, this goes by pi system. Clear? That is good. Now, we take a organic chemistry reaction and see what happens. For example, I have a okay, I can put the name also, like R, I do not want R, I can put an acetone and treat it with isopropanol. So, what how to write this reaction and what product we can expect out of this, we will just see. Okay. Whether just for introduction, how to do this chemistries. I have an acetone. So, how you write this? First, you have an acetone. You will say that you can directly you can say that can say it is singlet. So, this is the way you have to write. Okay. Do not write the reactions directly. Okay. That goes in it. Okay. Or you can write as T, or you can. So, you have now created a radical like this. Okay. You have a system where you have an isopropanol. You have like I can have a system like this, isopropanol, right. So, first question is that what type of reaction it is. It is whether it is an among this 5 class, what class is this, like whether it is an electron transfer, yeah, it is an hydrogen abstraction reaction. So, first you come to that conclusion, yes, it is an hydrogen abstraction reaction. Now, it has possibility here to abstract many hydrogens, right. I have an hydrogen here, okay. This you can call A. I have an hydrogen from here which I can B. This hydrogen will be the same that of that symmetrical. I have an hydrogen here which will be C. So, it is an option of abstracting this O dot can abstract any hydrogen from here, it likes. So, which it tries to prefer to abstract. If it tries to abstract your hydrogen A, then again you are generating an alkoxy radical, which is not favored, right. It is clear. That is how you say that it is not going to abstract that. For example, I have seen like if you have an methanol and do a photochemistry in methanol, okay. Most of the time people say that it abstracts hydrogen from that. You have a methanol, okay. You create a radical. So, that radical is going to abstract an hydrogen from where? From the methanol. Whether it is going to abstract that OH hydrogen or it is going to abstract Yeah, it will not, people think it goes and abstract your hydrogen from the OH. See, if you are going to abstract an hydrogen, you are generating a methoxy radical. So, it does not do that, it abstracts an hydrogen from your CH, okay, so that it gets a CS2OH, then it becomes formaldehyde. That is how photochemistry reaction goes. Same way, you cannot generate and it is very hard to abstract this hydrogen. Okay. Now, again you have a two choice here, you have B and C, you have to decide whether it is going to abstract this B hydrogen or its C hydrogen. Here you use your stability comes into the picture, right. If it is going to abstract the hydrogen from B, you are generating a CH2 dot radical. If I abstract an hydrogen from C, I am going to generate a C dot radical, that is, one is a type of secondary radical and tertiary radical, and you know which radical is stable. So, which radical is stable? Yeah. So, you try to abstract the hydrogen from C. Now, it looks like to be very easy, okay, but I will see the exam how it goes. People think like it is easier to find out which radical, okay. It is not that easy when you go for some bigger system. So, you get what product then? You get I get OH with my C dot, I get a CH3 here, okay. Same way I can get, once it gets abstracted, get my dot, right. So, you get this once the hydrogen abstraction takes place. Okay. Now, what happens? Yeah, now it undergoes a dimerization. With a system like this. So, I have taken an acetone. So, what happens second, if I write it properly, I have taken an acetone, see did my photolysis. See, if I write CH3, CHOH, CH3, okay, then at least you come in your mind that it is going to do an hydrogen abstraction. Most of the time we are not going to say that, we say that it is isopropanol, and you never think about the solvent at all. That is how, because in the first class I have written CH3, CHOH, and I am asking. If I am not, I am just writing isopropanol or anything, you will never think about that it is going to abstract an hydrogen from the solvent. Okay. So, that part is more important than if I do in isopropanol H mu, I get my nice product. So, this is your, so if I change this isopropanol, why I have taken isopropanol, you will know that to make this reaction very simple. If I change this from isopropanol to something else like tertiary butanol or whatever, then you have, in this case, see you have a your reactant, the radical which your reactant and your solvent both are same. That is why you can get a dimerization to give you one product. If this is, for example, is different, okay, then you think about this can have a, this itself can dimer to give me one product, this can dimer to give me another product, this and this can dimer to give me other product. So, you can end up with 3 different products in that case. That is how it becomes like tougher. For simplicity, we have taken isopropanol, so that it tries to give me only one product. But if I change the solvent little bit, then everything will be different. If I take a toluene, for example, then what happens, this radical will take that, you will get a bibenzyl type of products. You will get CS2 phenyl, then that CS2 dot phenyl will to give me bibenzyl, and this will give you dimer product, like that you can get n number of products. Okay. So, that where you should be little bit careful when you do your photochemistry. Okay. We will see one more, we will see another reaction which is also interesting one. Just to give you a glance, okay. But later on from next class we will take individual reaction and we will study in detail. This is just to give you a glance about this reactions, how it happens. Okay. Now, what happens? You have your carbonyl, same way it should become a practice of writing like this. That is why I am just trying to do it. N pi star transition, you get a singlet, then it gives you triplet. Let it become a practice, so that next time you can do not forget to do that. Now, we will see the reaction of this triplet. Okay. Now, you have an alkene and you have your O dot and C dot, right. So, you know this reaction because it is very clearly shown that it should be an addition to your pi system, right. Now, how this going to add up? Your O can take an electron from C, okay, and I can get this product, that is I can get this, okay, or I can say that I can also right. I can get any of this. I can get this guy or I can get, right. So, I just can change it down. It can form with this CS2, get me a radical here, okay. Otherwise, this can attach to this carbon and get me a radical here. So, I have two options now. So, which will be the better one? First one. Why? Stability of the newly formed radicals. See, that is where the photochemistry has the first part of your photochemistry has more link with your spectroscopy. Okay, if you are good in spectroscopy, you can know n pi star transition, pi star transition, that it covers. So, the photochemistry has more link with the spectroscopy, and once you go after your reactant, it is more like a free radical chemistry, like radical chemistry. If you are strong in radical, you can do the product studies. So, what happens here? If you see the photochemistry from triplet, the photochemistry is over. Photochemistry is done with triplet state, and after that I am doing only what? Radical chemistry. I am not doing any photochemistry here. Photochemistry is up to triplet, it gets triplet state, and then I have given you an insight that the reactivity will be on oxygen atom. That is the only photochemistry gives you a knowledge. After that, whatever you are doing is a sort of free radical chemistry. If you are good in radical chemistry, the other part also you are good. So, what happens once you, so we said that we said that we will get this, right. You get this. Now, tell me what is the, what will be the product? Cyclization to oxy-10. Any other suggestion from any other people? What are the products we can get? One, you said that it is nice that you say that this 2 makes a bond to give me this product, okay, whatever it is. Oh, I am missing my carbon there, sorry, CH2 I am missing there, CH2. So, I get this product, that is what you say. So, what radical is? That is what you are not looking about. What is this intermediate I? What is this intermediate I? It is what radical it is? I is? Huh? That is triplet state. This is intermediate, right? I, right? What intermediate we are getting here? It is a 1,4 diradical. So, what you expect from that guy? Just cyclization, just or anything more we can expect from this guy. Just think. Bond breaking means I will get back again my static material, right? I can get to my ketone and I will get my alkene. That is will be my starting material. That's what. Yes. Why you are omitting that? Because I said it is addition to pi system, so your mind doesn't open up for that. See, even that will be little bit tricky if you see. For example, I take this O. See, most of the time if I write this, you can find it out. It does not work like that. No? So, I have a radical here, right. So, this radical what it does can take this hydrogen, right, yes or no. So, that I get this. So, you will get what? Can you get this product? It looks like to be simple, it is just to understand. I am not doing any big chemistry here. Right. Any other thing, any other product you can think about? So, one we cyclized, okay. Another we abstracted this radical abstraction hydrogen from here. Okay. Why cannot this radical can abstract an hydrogen from here? Why you are taking that chance out? Because if you see that will be different product. Just write that, you write that product, you will know that it is different. OCS2. See, the arrow should be off headed, because you are doing a radical chemistry. So, you get a different product, right. You have a double bond now to the CH2. So, if I take then if I write the reaction, I have an acetone. See, it looks to be a very simple reaction. You have an acetone plus you have an alkene to a reaction. So, you get like O. So, you get 3 products basically, simple chemistry. See, even I have taken the simplest molecule now, and I am saying that I can think about 3 products. I can take, there are many good reactions where you can keep on writing a number of products, and it happens when you do a reaction in the lab. Organic photochemistry gives like 3 or 4 reactions products. Okay. So we will take one more reaction which you guys know for sure. Write this one, which is one. So what happens in this reaction? Any idea? What reaction it can be? Yes. Oh, I have not written properly. Huh? Oh, it's not there. So you have a, you have a ketone, you have a benzophenone with your ortho position with an hydroxy molecule, right? So if I shine light, what you can look for? One, that all we know that we can write up to my triplet states, that is from singlet you can always write your triplets, that is all fine, that you can write on singlet, then you can write your triplet. Just think about writing a triplet state now. It gets excited. What happens? Any idea? You want me to? I can put your dot. Okay, dot here. That's your triplet state. What you can now expect?
So what is the singlet state?
Singlet state is again, that's you don't have a radical. That's same. I am not writing the spin. I am just writing at singlet, and this is your triplet, right? Just the spin about. All the time we write this. So you write an H mu, you write a singlet, then you write your triplet states. It about all this singlet and triplet is based on your spin. Now what happens after this? Yes, this will abstract. So it's an hydrogen intramolecular hydrogen abstraction. So just write that, what you get. You get your, just write, if you can get it, it will be nice. Can I write this? O dot O, my O hydrogen O dot. So you get this part, right? Is there? Are you guys getting this? So what happens this then? Does cyclization? Where it does the cyclization? This you want to make a, this it is possible. It will be a highly strange one, right? Molecule doesn't like to do that. Yes, sir. Again ketone.
The double bond is break and O.
Yeah. So we always never look into our aromatic ring. Na? Can you look into your aromatic ring? right, you get this. Fine, this is stable now. So, what it does again? Huh? Tetramerized to back what? Where? Keto form, can you write that keto form, how it looks like? Write that keto form and say me how it looks like. This is looking like your starting material. Yes. So, you start from here and you see this, why it is, this type of molecules are very important. It does intramolecular hydrogen abstraction very fast and it gives back. So, where you can use this, see this molecule, it takes the photon, okay, and uses the photon, but again gives you the starting material back. So, where you can use this? Catalysis. Photo? You want to use it as a photosensitizer or what? It is not sensitizing anything. See, it is taking the light and it is using it, and anywhere it has a very good application. Energy transfer doesn't have. It is one of the best photostabilizer. Okay. See, if you want some molecule doesn't, you do not want that molecule to get any active molecule, you do not want that to be degraded by light. So, you take this and put it into it. What it does? It takes the light, it does the chemistry, it uses up and gives the same starting material, takes that. So, the active ingredient, which is like, for example, I am taking a molecule which is photolabile, okay, and it is a very active molecule. I want to use it in the sunlight or something like that. That time if I take it and formulate and take it in the solution, it is going to degrade. So, what I do? I put some photostabilizer in it. So, that this photostabilizer will take all the light and does this chemistry, goes around and around, but it utilizes the photon properly, and so that my active molecules is not disturbed. This is a very good photostabilizer and it is a good example for your intramolecular hydrogen abstraction. So, you have many good applications which you can start doing from photochemistry. You can see the reactions look like very simple. I am not taken any complicated reaction so far. We are taken a system. First case, I have taken a simple reaction where I have taken acetone. Okay, I have taken acetone and did an N-pi star chemistry. Nothing big I did. First N-pi star chemistry. This is an proper hydrogen abstraction reaction, that is from intramolecular, and the photochemistry is nothing there. It is more about your free radical knowledge. If you know the free radical knowledge, you are ending up with the product. And then what I did is that I took my pi-pi addition, alkene chemistry. Then we discussed little bit about alkene chemistry, how this works. Okay. And finally, we did intramolecular hydrogen abstraction reactions. So, like that you can there are many reactions, like I said 5 class. So, what we will do initially, for example, you have an acetophenone, it can do some alpha cleavage reactions. You have a cyclohexanone type of systems, for example, I have a cyclohexanone or a cyclopentanone. And if I shine the light, what chemistry you expect here? Dimer happens. Cleavage of alpha. It undergoes a very nice alpha cleavage because the ring is strained. It undergoes an alpha cleavage reaction. So, so this is a type of example. So, that is what I said, like we will take now, what we will do is that we take an individual reactions. First we will try to understand the theory, that will spend at least 1 hour to understand. Like if I take an alpha cleavage reaction, I will say that why it should undergo an alpha cleavage, what are the criteria you should know that it should undergo alpha cleavage, whether the radical should be stable or thermodynamically it is allowed process. Once we discuss for 1 hour, then in the next 2 hours we will sit and do all the problems, and I will give assignment based on the alpha cleavage reaction. Once we are completely sure that we can do alpha cleavage reaction, then we move to our hydrogen abstraction. Your Norrish type 2 reactions all come into that picture. Then once we cover that, then addition to pi system. Addition to pi systems are very interesting because it depends sometimes more on the alkene. If I take an electron withdrawing alkene, like electron deficient alkene, and if I have an electron rich alkene, whole chemistry of addition will change. Okay, that part we have to discuss. Then we slowly go to our energy transfer reaction, that is sensitizer, quenchers, all this comes there. How to sensitize a reaction, how to quench a reaction. Okay, then we do electron transfer reactions, PET chemistry. Your photo-induced electron transfer reactions, which is now like getting more hardcore in research, right? PET chemistry, photo-induced electron transfer reactions. That all we will discuss there. So these are the 5 main reactions we have to understand on n-pi star chemistry. Once we are done with this, then we can move to a pi star chemistry. Pi star chemistry, we will do some photochemistry there. I will teach you some pi star photochemistry, but then it will be moving towards your pericyclic reaction. You will have more pericyclic reactions with your pi star systems. Clear? Then one more, like which I want to teach you. Yeah. Pi symbol. We have to study one beta cleavage from n-pi star chemistry. That is also, it's a very small class of it, that is beta cleavage of n-pi star chemistry, that we have to study little bit. I will give you an example so that you can keep it in mind and understand how this chemistry works. You just take this example. Take this example. Okay. Since we are written some alpha cleavage here, okay, I want you to put some insight on this reaction and see whether what type of chemistry it can happen, whether you can see an alpha cleavage reaction here or you will think of something else. Just keep on whether you can do a cleavage here, okay, or can I do a cleavage, can I draw, can I do a cleavage here, that also can happen. So, in alpha, so there is one small class of that chemistry, that is beta cleavage chemistry, fine. So, from next class we will start studying 1-1 reaction, all 5 reaction with this small class of beta cleavage. So, these are the 6 reactions we are going to cover.